Tonight, somewhere in the sky above you, a star is being born. And somewhere else, in the dark between the galaxies, another is quietly coming to its end. Both of these things are happening right now, as they have for billions of years, in a rhythm far older than the earth beneath you. Every star that has ever shone had a beginning, and every one of them will have an end. And the quiet truth we'll sit with tonight is that those endings are not distant and unrelated to you. They are woven into the iron in your blood, the breath moving through your chest, the simple fact that you are here at all to wonder about any of it. Over the next little while, we'll follow that long story slowly and gently, from the cold and silent clouds where stars first take shape, through the steady calm of their lives, and on to the many ways they finally let go. Some of it is tender, some of it is almost unimaginably violent, and all of it is true. So let yourself grow still now. Let your shoulders soften and the weight of the day slide away, and let your breathing slow on its own. You don't have to hold on to every word. You can drift off whenever you like, and the stars will keep turning without you. So let's begin where every star begins, in the cold and in the dark. The iron in your blood was made inside a dying star. This is not a poem or a pretty turn of phrase. It is a plain, physical fact. Every atom of iron that carries oxygen through your veins right now, in the quiet of this moment, was forged in the heart of a star that lived its whole life and died long before the sun was ever born. The same is true of the calcium holding your bones together, the carbon at the center of nearly every part of you, the oxygen you're breathing slowly in and out as you rest. None of it began here on Earth. Almost all of it came first from the stars. To feel how strange that is, you have to travel back to the very beginning of everything. When the universe was young, and I mean truly young, in its first few minutes, there were no stars anywhere. There were no planets, no rocks, no living things. There was only a thin, hot fog spread evenly through all of space. And that fog was made of the simplest ingredients imaginable, mostly hydrogen, the lightest element there is, along with a good amount of helium and only the faintest whisper of one or two others. That was the entire inventory of creation. No carbon to build living things, no oxygen to breathe, no iron, no gold, no calcium. The early universe was beautifully, almost unbearably plain. So where did all the rest of it come from? Every heavier element, every atom more complex than those first few simple ones, had to be built somewhere. And in all the vast cosmos, there was only one kind of place with the heat and the crushing pressure needed to build them. The deep core of a star. A star, you see, spends its long life as a kind of furnace. In its center, hydrogen is squeezed and heated until it fuses together into helium, and that fusion is what makes a star shine. But as a star ages and its simplest fuel begins to run low, it learns to fuse heavier things. Helium becomes carbon, carbon becomes oxygen. Step by step, over millions and billions of years, the star works its way up through the elements, building heavier and heavier atoms in its core, the way a slow fire turns light kindling into something denser and deeper and more enduring. And then, for many stars, comes the ending. And the ending is where the real alchemy happens. When a massive star reaches the close of its life, it collapses and detonates in an explosion so bright it can briefly outshine an entire galaxy of billions of stars. In the unimaginable heat and fury of that death, the very heaviest elements are forged in moments. and then the whole rich harvest, the carbon, the oxygen, the iron, all of it, is flung outward into space, scattered across light years like seeds thrown from an open hand. And not every element in you was made the same way, or in the same kind of star. The carbon and oxygen that fills so much of you were cooked gently over long ages in the quiet cores of ordinary stars. The iron in your blood was forged in the fierce hearts of the heaviest stars and in their explosive deaths. And some of the rarest, heaviest things of all, the gold and silver that people have treasured throughout history, may have been made in events more violent still, in the unimaginable collisions of the burned-out cores of dead stars. Something we have only begun to understand in recent years. The matter in your body is not the work of any single star, but a gathering from many, a slow harvest of countless lives and countless endings, mixed together across billions of years and folded at last into you. For a long time, that scattered material simply drifts. It mixes into the thin gas between the stars, dust and atoms wandering through the dark for ages. But every so often, a cloud of that enriched material begins to gather itself together again, drawn inward by its own gravity. And out of that gathering, a new star is born. And around it, sometimes, new worlds. Our own sun is one of those later generation stars. The earth beneath you, the water in its oceans, the rock under your feet, your own body. All of it was assembled from the ashes of stars that lived and died before our sun even existed. So when someone tells you that you are made of stardust, they are not being sentimental. They are simply describing where your atoms have been. The iron in you was born in a stellar furnace. The oxygen in your every breath was cooked in the belly of a star. Even the hydrogen in the water of your body is older still. Most of it formed in the very first minutes of the universe itself. And it has been waiting all this time to become a part of you. There is something quietly staggering in that, my friend. You are not separate from the great story of the stars, watching it from a safe and distant shore. You are part of it. One of the ways the universe has, for a little while, of folding its oldest material into something that can look up and wonder. The atoms in your hand have seen the inside of stars. They are billions of years old. They will go on long after you, and one day, far in the future, they may find themselves inside something new. For now, though, they are yours, resting here in the dark, breathing slow. Stardust, gathered for a time into the shape of you. Stars are born in the coldest places in all the universe. It seems as though it should be the other way around. A star is the hottest thing most of us can picture. A roaring sphere of fire, pouring heat and light out across the emptiness. Surely such a thing must be born somewhere fierce and blazing. And yet the truth runs exactly opposite. The cradle of every star is a place of deep cold, deep silence, and almost perfect darkness. These cradles are enormous clouds of gas and dust, drifting slowly through the spaces between the stars. They are some of the largest single things in any galaxy. A single one can stretch across tens, even hundreds of light years, so vast that light itself, the fastest thing there is, would take longer than a human life to cross from one side to the other. They hang in the dark like continents of mist, glowing faintly at their edges, utterly black at their hearts. And they are cold, almost impossibly cold. Deep inside one of these clouds, the temperature falls to just a few degrees above the lowest temperature nature allows, the absolute zero where nearly all motion ceases. It is far colder there than the coldest night that has ever fallen on Earth, colder than anything you could ever touch and survive. In that frigid stillness, the thin gas grows so quiet that delicate molecules can form and hold together, drifting undisturbed for ages. The dust mixed through these clouds is worth picturing too. It is not dust like the kind that gathers on a shelf. These are unimaginably tiny grains, far smaller than a wisp of smoke, flecks of carbon like soot, and grains of silicate like the faintest powder of sand, each one built and scattered by stars that came before. There are countless trillions of them, spread thin through the cloud, and together they are so good at blocking light that they swallow the glow of whatever lies behind. And yet, for all their darkness, these clouds are emptier than almost anything we could ever build. The gas within them is thinner than the finest vacuum ever made in any laboratory on Earth, so sparse that, handful for handful, is closer to nothing than to something. The trick is simply how vast they are. Spread that whisper-thin gas across hundreds of light years, and the total gathers into a staggering sum, enough material in a single great cloud to one day build thousands upon thousands of stars. It is one of the quiet wonders of the cosmos, that something so close to empty, simply by being so unthinkably large, can cradle the makings of 1,000 suns. If you could somehow stand at the edge of such a cloud, you would see almost nothing at all, only a wall of darkness, vast and soft and silent. And you can actually witness this for yourself. On a truly dark night, far from any city, look up at the long band of the Milky Way. The dark rifts and patches that seem to tear gaps in that river of stars are not empty gaps at all. They are these very clouds, near and cold and immense, quietly blotting out the light from behind them. The most famous of them, the great nursery in the constellation of Orion, hangs there in plain sight as a faint smudge below the hunter's belt, a place where new stars are being kindled even now. Here's the quiet paradox at the heart of it. That deep cold is not an obstacle to making a star. It is the very thing that makes a star possible. To see why, picture the gas inside one of these clouds. Every cloud lives caught in a slow, endless tug of war. Its own gravity is forever trying to pull it inward, to gather it together and make it collapse. But the gas also carries warmth and motion, and warmth pushes outward, holding the cloud up and apart, resisting the squeeze. As long as the gas stays warm enough, that outward push wins, and the cloud simply drifts, stable and unchanging, for a very long time. But when the gas grows cold, truly, deeply cold, that outward push fades away. The motion slows, the resistance weakens, and now in the stillness, gravity can finally begin to win. A cold cloud is a cloud that can fall inward, gather, and one day light a fire at its center. The chill is what allows the collapse to begin. Without the cold, there would be no stars at all. So the warmest, brightest things in existence begin in the coldest, darkest, stillest places we know of. The fire that will one day pour across the void is conceived in frost and silence. There is something almost tender in that. The thought that the fiercest light needs a quiet, cold beginning, that brilliance starts in the deepest dark. For now, though, the cloud simply drifts, vast and silent and cold, light years across, holding within it the seeds of suns that have not yet begun to shine. No fire yet. No warmth, only the dark and the slow gathering, and all the time in the world. For millions of years, the cloud does nothing at all. It simply drifts, a vast, cold expanse of gas and dust hanging in the dark between the stars, perfectly content to remain exactly as it is. It could go on this way for an age, unchanged, neither growing nor collapsing, held in a long and patient balance. And in many cases, that is precisely what happens. A cloud can wait, silent and still, for longer than the Earth has existed, without ever giving birth to a single star. So something has to change. Something has to reach in and tip that balance, to give the cloud the smallest push toward falling inward. The question of what does the pushing is one of the quiet mysteries of how stars are made, and it is a question astronomers are still working to fully answer. Often, more than one thing seems to play a part, and it can be hard to say which gave the decisive nudge. There are a few culprits we know of. Sometimes two of these great clouds, wandering slowly through the galaxy, drift into one another, and the gentle collision presses their gas together until parts of it begin to collapse. Sometimes a cloud passes through one of the bright spiral arms of its galaxy, where the gas is naturally crowded and compressed, and that extra squeeze is enough to set things falling. And sometimes, most dramatically of all, the push comes from the death of another star. This last one is worth resting on for a moment. When a massive star reaches the end of its life, it explodes, hurling its outer layers into space at tremendous speed. That blast spreads outward through the surrounding darkness like a ripple moving across still water, a vast shell of gas racing into the spaces between the stars. And if that expanding wave happens to reach a cold, quiet cloud nearby, it presses into it like a hand into soft clay. The cloud is compressed, its gas is driven together, and in the places where it is squeezed hardest, gravity finally takes hold and the slow collapse begins. Think about what that means. The death of one star can be the very thing that calls new stars into being. The ending becomes a beginning. A star that has lived out its entire life and let go in a final burst of light reaches across the dark and stirs a sleeping cloud awake. And from that stirring, new suns are born. There is a kind of inheritance in it. One generation of stars seeds the birth of the next, not only with the elements they forged, but with the very push that sets the next generation falling into place. We even have reason to think something like this may have happened at the birth of our own sun. Tucked inside the oldest rocks of our solar system, in ancient meteorites that have survived since the very beginning, scientists have found the faint traces of certain rare materials, the kind that are made only in the hearts of exploding stars, and that do not linger for long. Their presence is a clue, a hint that a nearby star may have died not long before our sun was born, and that its death may have helped trigger the collapse of the cloud that became our home. This is not certain. It remains one possible story among a few. But it is a real and serious idea, and it carries a quiet wonder of its own, that our sun and the earth and you may owe your existence in part to the death of a star whose name we will never know. And when a cloud is finally tipped into collapse, it rarely makes just one star. A single great cloud, once it begins to fall, tends to break apart into many smaller knots, each gathering inward on its own, so that stars are most often born not alone, but together, in broods of hundreds or even thousands at a time. They form as siblings kindled side by side from the same dark cradle, before the slow turning of the galaxy gently draws them apart over the ages, scattering them across the sky until each one drifts alone. Even our own sun, most likely, was born among such kin, brothers and sisters long since lost to the great drift, wandering the galaxy now, unrecognized and far away. It is humbling to sit with the thought that beginnings so often need an ending to set them in motion. That stillness sometimes has to be broken before anything new can grow. That a cloud might wait, patient and unchanging, for an age, until at last something reaches in from far away and whispers, gently, "Now." And when that moment comes, it is almost imperceptible. There is no sudden flash, no great event to mark it. Somewhere deep in the dark, in a cloud light years wide, a faint shiver passes through the gas. A region that had been holding itself apart begins, ever so slowly, to fall inward toward its own center. Nothing about it looks like a star yet. It will take a vast stretch of time before it does, but the long gathering has begun, and in the quiet of the dark, the first stirrings of a new sun have been set in motion at last. Once a cloud begins to fall, it falls for a very long time. There is nothing sudden about the birth of a star. The collapse that makes one unfolds across hundreds of thousands of years, slow beyond anything we can easily feel. A gathering so patient that in any single human lifetime, you would never see it move at all. And yet, move it does. Pulled by its own gravity, the gas in one corner of a great cold cloud begins to drift inward, every part of it falling gently toward a common center, like snow settling toward the bottom of a deep and silent well. As the gas falls, something quietly remarkable happens. It begins to grow warm. This is one of those simple truths of nature that feels almost magical when you first meet it. When things fall together and squeeze, they heat up. The gas at the center is pressed harder and harder by everything piling in around it, and under that mounting pressure, the cold begins to lift. A faint warmth kindles in the heart of the collapsing cloud, deep inside its dusty shell, hidden from view. This warm, growing core has a name. We call it a protostar, a star in the making, not yet truly shining, but no longer merely cold gas. It glows softly in a kind of light our eyes cannot see, a deep infrared warmth buried in the dark. If it seems strange that simply falling together should make a thing grow hot, you have felt a small echo of it yourself. Press the air down in a bicycle pump, and the pump grows warm beneath your hand. Squeeze anything tightly enough, quickly enough, and it heats. In the collapsing core of a forming star, that same plain rule plays out on an unimaginable scale. The weight of an entire cloud bears down on the center, pressing the gas there harder and harder, and the temperature climbs and climbs. What began as some of the coldest material in the universe slowly turns warm, then hot, then hotter still, all of it driven by nothing more than the patient, relentless pull of gravity gathering everything inward. And as the cloud draws inward, it does something beautiful. It begins to spin. Every cloud carries some faint, lazy turning to begin with, far too slow to notice. But as it shrinks, that turning speeds up, the same way a skater pulls in her arms and spins faster, or water swirls quicker as it nears the drain. The gathering cloud whirls more and more rapidly, and that spinning flattens it. What was once a shapeless blob is pressed, over time, into a broad, slowly turning disk, with the warm young protostar glowing at its very center. That disk is where the star takes its meals. Gas and dust spiral slowly inward across it, drifting down onto the growing core, feeding it, adding to it, helping it swell and warm. And in the outer reaches of that same disk, far from the center, something else is quietly beginning. The leftover dust and grains begin to clump and stick and gather, the first faint seeds of what may one day become planets. The very disk that feeds a newborn star is also the place where worlds are sown. There is one more thing the newborn does, and it remains one of the lovelier puzzles in all of this. Even as it draws gas inward, a young protostar fires two great jets of material straight out from its poles, narrow beams of gas flung into space in opposite directions, racing outward for light years, lighting up where they strike the surrounding cloud. We can see these jets glowing across the dark in many a stellar nursery. And yet exactly how a forming star launches them is something we still do not fully understand. We believe it has to do with magnetic fields, twisted and wound up by all that spinning, flinging some of the gas away, even as the rest falls in. But the full picture is still being worked out. A newborn star, it seems, breathes out as it feeds, and we are still learning how. Sit for a moment with the shape of what is happening here. Out of a cold, formless, drifting cloud, with no plan and no hand to guide it, order is quietly emerging in the dark. A center forms. The whole gathers itself into a turning disk. A warmth kindles where there was only chill. Worlds begin faintly to take shape in the outer rings. All of it arises simply from gravity and time and the slow, certain pull of things toward one another. There is a kind of grace in that something so structured and so finely arranged should come all on its own out of so much shapeless dark. And so the long gathering continues, hidden away inside its dusty veil. A soft glow at the center, growing warmer with each passing age. A great disk turning slowly around it, feeding it grain by grain. Two faint jets reaching out into the night. Not yet a star, not quite, but something gathering itself, patiently, toward the moment it will shine. For now it rests there in the dark, warm and turning, taking its time, with no need to hurry toward anything at all. There is a single moment when a ball of gas becomes a star. For all the long ages of gathering and falling and slow warming that come before it, the true beginning of a star comes down in the end to a threshold, a line that is crossed in the deep heart of the collapsing cloud. On one side of that line there is only warm gas, glowing faintly, pressed together but still dark. On the other side there is a star, truly a light, shining with its own fire. And what carries it across is heat, simply heat, rising and rising in the core until it reaches a number that changes everything. That number is around 10 million degrees. As the heart of a forming star is squeezed tighter and tighter by all the weight pressing in from above, its temperature climbs past anything found on Earth, past the heat of any flame you've ever felt, on and on until the very center reaches that staggering threshold. And there, at 10 million degrees, something new awakens. The cores of hydrogen atoms, packed in unimaginably close and moving unimaginably fast, begin to slam together and fuse, merging, joining, becoming helium, and releasing a flood of energy as they do. The fire at the center of a star has been lit. Fusion has begun, and it will not stop in many stars for billions of years. This is the moment of ignition, the instant a gathering of gas finally earns the name of star. And from that instant onward, everything about the object changes. Before it was only falling inward, collapsing under its own weight with nothing to hold it up. But now, with fusion burning at its center, a great outpouring of energy pushes outward from the core, pressing back against all that crushing weight. And those two mighty forces, gravity pulling endlessly inward and the fire pushing endlessly outward, settle into a balance. That balance is the secret to a star's long life, and it is worth pausing to take in just how exquisite it is. Picture it. gravity, immense and tireless, forever trying to crush the star down into nothing. And against it, the heat of fusion, forever pushing back out, trying to blow the star apart. Neither one wins. They hold each other in a near-perfect standoff, poised against one another so finely that the star neither collapses nor explodes, but simply holds its shape and shines. A star is not a still or settled thing at all. It is a balance, a truce between two opposing powers, held steady for an unthinkable span of time. And the wonder of it is how stable that truce can be. Should the core ever burn a touch too hot, it swells outward just slightly, which cools it and gently slows the fire back down. Should it cool a touch too much, gravity presses in a little harder, which warms it and coaxes the fire back up. The star corrects itself over and over, without thought or effort, settling always back toward balance. It is this quiet self-steadying that lets a star shine on, calm and even for ages on end. A fire that tends itself, trimming its own flame, holding its own light steady across the dark. Our own sun has been holding that balance for nearly 5 billion years, and it is doing so this very moment, while you rest. In its core, every single second, it fuses hundreds of millions of tons of hydrogen into helium, an outpouring of energy almost beyond words, and yet so perfectly matched by the inward pull of the sun's own weight that the result seen from the outside is simply a calm and even light. The sunlight that warms your face on an ordinary afternoon is the gentle surface of that titanic balanced fire, a fury held so steadily in check that it reaches us as nothing more than warmth. When a young star first reaches this balance, we say it has settled into the long, stable prime of its life. The frantic gathering is over. The collapse has ended. The dusty veil that hid it begins slowly to clear away, and at last the new star's light breaks free and shines out into the surrounding night for the first time. After all that falling in the dark, after all that patient warming, the star simply begins quietly to do the one thing it will now do for almost all the rest of its existence. It shines. There is a kind of peace in that settling. After the long unrest of being born, all that falling, all that gathering, all that mounting heat, the new star comes to rest in a balance it can hold for billions of years. Two vast forces, gravity and fire, no longer at war but somehow at ease with one another, leaning into each other so gently that the result is simply a steady glow. A newborn sun finding its balance in the dark and beginning the long, calm work of shining. Some stars never quite manage to be born. In the same cold clouds where suns are kindled, there are objects that came so close to becoming stars, and in the end fell just short. They gathered, they collapsed, they warmed at the center, exactly as a true star does. But they could not quite gather enough, not quite enough weight, not quite enough heat to cross that final threshold and light the steady fire of fusion at their hearts. And so instead of blazing into stars, they became something stranger and quieter. We call them brown dwarfs, and they are, in a sense, the universe's almost stars. The difference comes down to mass, to how much material an object manages to gather as it forms. To truly become a star, to kindle the lasting fusion that lets it shine for ages, an object needs to pull together a great deal of gas. There is a kind of minimum, a lower limit, below which the core simply never gets hot enough, no matter how long it waits. That limit sits at roughly 8% of the mass of our sun, which still sounds enormous and is, but in the language of stars, it is the barest minimum. Gather less than that, and the central fire never properly catches. The object warms and glows, and then can only slowly cool. A brown dwarf lives in the strange country just below that line. It is far heavier than any planet, many tens of times the mass of a world like Jupiter, yet still too light to be a true star. For a brief while in its youth, it can manage a faint, partial sort of fusion, burning through a rare and delicate form of hydrogen that ignites more easily than the ordinary kind. But that special fuel is scarce, and it does not last. Before long, it is spent, the faint inner fire sputters out, and the brown dwarf is left to do the only thing left to it, to glow softly from the warmth of its own making, and to cool very slowly across billions of years. If you could see one up close, it would not look like a star at all. It would be a dim, sullen ember, glowing a deep and dusky red, or fainter still. Some of the coolest are so gentle in their warmth that their surfaces are barely hotter than a cup of tea, or no warmer than a summer's day. They shine mostly in light our eyes cannot catch, a quiet infrared warmth radiating into the dark. And because they are so faint, they are remarkably hard to find. The space around us may be scattered with them, drifting unseen and unremarked. And only in recent decades have our instruments grown keen enough to begin picking them out of the dark, one dim shape at a time. It was not until late in the 20th century that we found the first one for certain, glimpsed at last as a faint companion beside another star, a discovery that proved these in-between objects were truly out there and not merely a possibility on paper. Since then, we have found a great many more, and we have come to suspect they are remarkably common, drifting in great numbers through the dark spaces between the stars. A whole shadow population of almost stars, too faint to have ever caught our eye, quietly filling the night. There is a real puzzle, too, in saying exactly where a brown dwarf ends and a giant planet begins. The line between them is genuinely blurry, and astronomers still debate just where to draw it. Both can be cold and dim. Both can be wrapped in clouds and storms. The deepest difference lies in how they were born, whether an object gathered directly out of a collapsing cloud, the way a star does, or whether it grew slowly within the disk circling some other star, the way a planet does. But from the outside, a heavy planet and a light brown dwarf can look maddeningly alike, and telling the two apart is not always a simple thing. It is hard not to feel something gentle, almost wistful, toward these objects. They are the ones who came so close. They began exactly as stars begin, with all the same gathering and falling and warming, and they reached for the same fire every star reaches for. They simply did not have quite enough to grasp it, and rather than flaring into brilliance and then dying in some grand display, a brown dwarf does neither. It only fades, endlessly, patiently, growing a little dimmer and a little cooler with each passing age, for spans of time longer than the universe has yet existed. There is no ending for it, no final act, only a slow and quiet dimming that goes on and on and on. And so they drift out there in the dark, the almost stars, too grand to be planets, too faint to be suns, glowing with the last warmth of a fire that never fully caught, cooling so slowly that, on any scale we can feel, they seem hardly to change at all. Dim embers, alone in the great dark, holding what little light they have, and letting it go so gently you would never see it fade. The biggest stars die the youngest. It is one of the strangest truths in the whole life story of the stars, and it runs against everything our instincts tell us. You would think that a star with more fuel would live longer, that the great, heavy, brilliant giants with so much more material to burn would shine on for far greater spans than the small and modest ones. But the opposite is true, and dramatically so. The most massive stars live the shortest lives of all, and the smallest, faintest stars are the ones that endure, almost without end. To understand why, picture two stars side by side. One is a giant, many times the mass of our sun, hundreds of times brighter, a fierce blue-white beacon blazing in the dark. The other is a small red star, a fraction of the sun's mass, glowing dim and cool and quiet. The giant does indeed hold far more fuel, but it burns through that fuel at a furious, almost reckless pace, pouring out light so lavishly that, for all its greater store, it empties itself astonishingly fast. The little red star, by contrast, is endlessly frugal. It sips at its fuel, burning so gently and so slowly that it can keep its small flame alive for an almost unimaginable length of time. The numbers, when you hold them up, are staggering. A star several times heavier than the sun may burn through its entire life in only a few tens of millions of years, a mere flicker by the measure of the cosmos. The very largest stars, the rare and enormous giants, can race through their whole existence in just a few million years, flaring brilliantly and then dying while the universe around them has scarcely aged at all. Our own sun, a modest middleweight, takes a far gentler path, something close to 10 billion years from birth to death, with roughly half of that still ahead of it. But the small red stars are the true champions of endurance. The faintest of them can shine on for hundreds of billions, perhaps even trillions of years, far, far longer than the entire age of the universe so far. And here's a thought that is almost difficult to hold in the mind. The universe, as best we can tell, is somewhere near 14 billion years old. That sounds like an eternity, and yet it is not nearly long enough for even a single one of those small red stars to have reached the end of its life. Not one. Every dim red dwarf that has ever formed in all the long history of the cosmos is still out there shining, with vast ages of life still ahead of it. They are so frugal, so patient, that the universe itself has not yet existed long enough to watch even the oldest of them grow old. They will still be glowing quietly long after stars like our sun have come and gone. There is a way to read this whole story written right into the colors of the stars if you know how to look. The color of a star is a quiet announcement of how hot it burns, and so, in its way, of how it will live and die. The blue-white stars are the fierce and massive ones, blazing hottest, doomed to the shortest lives. The yellow stars, like our own sun, burn cooler and steadier and last far longer. And the deep red stars are the coolest and smallest, the frugal ones, the ones that will outlast nearly everything. So on a clear night, when you find a star with a faint blue cast, you are gazing at something brilliant and fleeting. And when you find one glowing soft and red, you may be looking at a star that will still be shining long after the blue one, and the sun and perhaps even the earth have faded into the dark. There is a quiet lesson hiding in this, if you care to find one. The brightest stars, the ones that burn most fiercely and shine most gloriously, are precisely the ones whose lives are shortest. Their brilliance is bought at the price of their brevity, and the small, dim, unremarkable stars, the ones that would never catch your eye, that glow so faintly you might never notice them at all, are the ones that endure almost forever. It is a strange arithmetic, and not always a fair-seeming one, that splendor and longevity should pull so firmly in opposite directions that to shine the brightest is somehow to burn out the soonest. You can picture them together, the two ends of this great divide. The brilliant giant, blazing blue-white and furious, magnificent and doomed, pouring out more light in a single moment than its small cousin will manage in an age, and destined to be gone in the blink of a cosmic eye. And beside it, in the mind's eye, the little red ember, modest and slow and almost shy in its faint glow, asking so little of itself, that will still be quietly burning long after the giant has died, long after our own sun is gone, perhaps long after almost everything else we know has faded into the dark. It is a gentle thing to rest on here in the quiet, that the loudest light goes first, that the softest endures, and that somewhere out there, even now, a small red star is shining its patient, frugal shine, utterly unhurried, in no danger at all, with more time ahead of it than the whole history of everything that has yet come to pass. For almost the whole of its life, a star does nothing dramatic at all. We love to tell the story of how stars are born, with all its gathering and collapsing and the first great kindling of fire, and we love to tell the story of how they die, with all the drama that brings. But between those two bright moments lies something we rarely speak of, something far longer and far quieter than either. The vast middle, the long, calm prime of a star's life, when it simply shines, steady and even, asking nothing and changing almost not at all. And when I say this middle is long, I mean it is long beyond any easy reckoning. For a star like our sun, the fierce drama of birth is over in a cosmic eye blink, and the drama of its eventual death will be over quickly too. But the calm stretch in between lasts something close to 10 billion years. 10 billion years of just shining. It is by far the greatest part of any star's existence. So much so that if you could glance at the sky at some random moment in the long history of the universe, nearly every star you saw would be living out this quiet, steady middle, neither being born nor dying, simply burning on. Our own sun is there right now. It is something like 4.5 billion years old, which means it has already spent a span of time we can hardly imagine doing nothing more than this: rising and setting, warming the earth, holding its planets close, pouring out the same gentle light morning after morning, and it sits, as best we can tell, at roughly the midpoint of its calm. Around half of its long, steady life is behind it. Around half still lies ahead. The sun, in a sense, is in the unhurried middle of its days. What makes this possible is a balance held with extraordinary patience. Deep in the star's core, fusion pours energy outward, and that outward push presses back exactly against the inward pull of the star's own enormous weight. The two forces lean against each other so evenly that the star neither swells nor shrinks, but simply holds its shape and glows. And the truly remarkable thing is how forgiving that balance is. Should the core ever burn a touch too hot, the star eases outward just slightly and cools itself back down. Should it ever cool a touch too much, it settles inward just slightly and warms itself back up. Over and over, without thought, without effort, the star corrects itself, nudging always back toward steadiness. It is this quiet self-tending that lets a star shine on, calm and even, for ages without end. That is not to say nothing changes at all. Across these vast spans, a star like the sun does brighten, very slowly, so slowly that the change would be utterly invisible across any human life. or even across the whole span of human history. When the sun was young, long before the earth had oceans or air worth breathing, it shone noticeably fainter than it does today, and it will go on brightening by the gentlest of degrees across the ages still to come. But this is change measured against the clock of the cosmos, not against ours. To anything that lives and dies as quickly as we do, the sun is simply constant, the same warm presence it has always been. And it is worth remembering what that long steadiness makes possible. Life, as far as we know it, needs time, vast and unhurried time, to take hold and unfold. It took billions of years for the first faint living things on Earth to slowly become forests and creatures and eventually us. None of that could have happened around a star that flickered or flared or changed its mood from age to age. It could only happen around a star content to shine the same way, gently and reliably for an almost unthinkable span of time. The long calm of a star is not merely an empty waiting. It is the very stillness in which worlds grow quiet enough and steady enough for life to slowly begin. There is something quietly moving in that constancy if you let yourself feel it. We tend to be drawn to the dramatic moments, the beginnings and the endings, the flares and the collapses. Those are the stories worth telling, we think. And yet the deepest truth of a star's existence is not found in those rare and violent instants. It is found here, in the long calm, in the patient, faithful, almost uneventful work of simply shining, held steady for billions of years. Most of what a star ever is, it is quietly. And so the sun goes on, as it has for an age, and as it will for an age more. The same light it gave to the first living things in the sea. The same light that will fall on whatever comes long after us, rising and setting, warming and holding, asking for nothing. A steady glow in the dark, kept faithfully alight in the long and unhurried middle of its days. By the strict rules of physics, the sun should not be able to shine. It is a strange thing to say about the most familiar object in our sky, the very source of nearly all our light and warmth. And yet, if you take the ordinary common-sense laws that govern the everyday world and apply them carefully to the heart of the sun, you reach a baffling conclusion. The sun's core, hot as it is, simply is not hot enough to burn. By those rules, it should be dark. To see the problem, you have to look at what fusion actually asks of the matter inside a star. The sun shines by pressing the tiny cores of hydrogen atoms together until they merge and become helium, releasing energy as they join. But these cores each carry a positive electric charge. And you may remember, perhaps from playing with magnets as a child, how stubbornly like charges push one another apart. The closer you bring two of them, the harder they shove back. To force two hydrogen cores close enough to actually merge, you have to overcome that fierce repulsion, and that takes tremendous speed, which is to say, tremendous heat. The center of the sun is staggeringly hot, somewhere around 15 million degrees. You would think that would be more than enough. But when you do the careful arithmetic, you find that even at 15 million degrees, the hydrogen cores are moving far too slowly. They approach one another. They feel that mounting electrical shove, and they are turned back long before they ever touch. By the plain rules of the everyday world, the particles in the sun's heart should simply bounce off each other, again and again, forever, and never fuse at all. The fire should never light. And yet the sun shines. So what is really happening? The answer lies in one of the deepest and strangest truths we have ever uncovered about reality, a truth that only reveals itself at the very smallest scales of nature. Down in the world of the tiniest particles, things do not behave with the solid certainty we are used to. A particle is not quite a hard little ball sitting in one definite place. It is something blurrier, hazier, more like a faint smear of possibility, spread thinly across a small region of space. And because of that haziness, a particle can sometimes turn up where it has no business being. It can appear on the far side of a barrier it never had the energy to climb over. This gentle ghostliness has a name. We call it tunneling. Picture a ball that does not have enough push to roll up and over a hill, and yet every so often simply finds itself on the other side, as though it had quietly slipped through the hill rather than over it. In the world we live in, that never happens. But in the world of the very small, it happens all the time. And it is exactly what allows the sun to shine. The hydrogen cores in the sun's heart cannot, by rights, get close enough to merge. But every now and then, by the faint and patient magic of tunneling, one of them slips through the wall of repulsion it could never cross, and finds itself near enough to fuse after all. It almost never happens for any single particle. The odds in any one encounter are vanishingly small. But the sun's core holds an unimaginable number of particles, colliding an unimaginable number of times, and across all those countless tries, the rare miracle becomes a steady, reliable trickle. Enough fusion sparks to light a star, enough to warm a world, enough in time to make you. In fact, the whole process is so reluctant, so delicately improbable, that it unfolds with astonishing slowness, and that slowness is a quiet blessing. Because the sun burns its fuel so grudgingly, dribbling out its energy a little at a time rather than all at once, it can keep shining steadily for billions upon billions of years. A more eager star would have spent itself long ago. It is the very difficulty of fusion, the very fact that it should barely be possible at all, that gives the sun its long and gentle life. There is something humbling in this when you sit with it. The warmth on your face, the light that fills your days, the sheer ordinary reliability of the sun in the sky, all of it rests on a ghostly quantum trick. A faint slipping through that, by the rules we live among, should not happen at all. The most dependable thing in our world is built upon one of the least intuitive truths in all of nature. Reality, it turns out, is stranger and far more generous at its smallest scales than our ordinary eyes could ever guess. And so, deep in the heart of the sun, the quiet magic goes on, this very moment, as it has for ages. Countless tiny particles drawn close and turned away and drawn close again, and here and there, against all the odds, one of them gently passing through a wall it could never climb, joining with another and giving off a small flicker of light. Trillions upon trillions of those small flickers all together, becoming the steady glow that warms you now. The warmth on your skin today is far, far older than this morning. Sunlight feels like the most immediate thing in the world. You step outside, and there it is, falling on your face, warming your hands, seeming to arrive in the very instant the sun clears the horizon. It feels new, fresh, born just now. But the truth hidden inside that warmth is one of the loveliest in all of nature, and it has to do with deep, deep time. The light that warms you does, in one sense, arrive quickly. Once it leaves the bright surface of the sun and races across the emptiness toward the earth, it makes the whole journey, nearly 100 million miles of it, in only about 8 minutes. So the sunlight touching you at any given moment did indeed leave the sun's surface just 8 minutes ago. If the sun were somehow to vanish, you would go on feeling its warmth and seeing its light for those 8 final minutes before the sky went dark. But here's the secret. That 8-minute dash across space is only the very last easy step of a journey that began an unimaginably long time before. Because the energy in that sunlight was not made at the sun's surface. It was made far below, deep in the sun's core, where fusion burns. And getting out from that core to the surface, that is the hard part. That is the part that takes an age. To understand why, picture the inside of the sun not as open and clear, but as almost impossibly crowded and dense. The energy born in the core tries to travel outward, but it cannot fly straight. Almost the instant it sets off, it slams into a particle and is swallowed and then flung back out again in some random new direction. A moment later, the same thing happens, and again, and again. The energy does not journey outward so much as stagger, lurching this way and that, taking one tiny blind step after another through a dense and endless crowd, knocked off course untold trillions of times. It is a little like trying to cross a vast hall packed shoulder to shoulder with people, where every single step sends you caroming off someone new, so that for all your motion you drift outward only the slightest bit at a time. And the sun is enormous. So this blind, staggering, endlessly deflected passage from the core to the surface takes a length of time that is genuinely hard to believe. By some careful estimates, it may take many thousands of years. By others, far longer still, tens or even hundreds of thousands of years of bouncing and stumbling through the crowded dark, just to climb from the sun's heart to its shining surface. Only then, finally free, does the energy leap across space to reach you in its quick last 8 minutes. I should be honest with you about one thing, because the truth is even stranger than the simple version. It is not really one single ray of light that survives the whole long passage. As the energy is swallowed and flung out over and over, it is changed and handed along from particle to particle, like a message whispered down an endless line. So it is the energy itself, more than any single unchanging beam, that carries this deep antiquity within it. But that makes the wonder no smaller. The warmth you feel still rose from a fire that was burning before this morning by an almost incomprehensible stretch of time. Let yourself sit with what that means. The light that warms your face today may have begun its slow climb out of the heart in an age when great sheets of ice still lay across much of the earth, when the world looked utterly unlike the one you know, and no city and no written word yet existed anywhere upon it. That ancient energy has been working its way patiently outward through all the years since, through the whole long sweep of history, only to surface at last and cross the final gulf and arrive gently on your skin here, now, in this quiet moment. There is a strange tenderness in being warmed by something so old. We think of sunlight as the very emblem of the present, of bright mornings and fresh beginnings. And yet every warm ray carries within it the patient labor of the distant past, a journey begun in a time long before anyone was here to feel it. The sun is, in a way, always reaching us out of its own deep history. So the next time you stand in the sun and feel that simple, ordinary warmth settle over you, you might remember what it truly is. Not something new at all, but something ancient. Energy that waited an age in the crowded dark, stumbling slowly toward the light, so that one day, long after it set out, it could rest for a moment, soft and warm on you. When the sun finally runs out of fuel, it will not fade quietly away. It will swell. This is one of the great surprises in the life story of a star. We tend to imagine that when a fire runs low on fuel, it shrinks and dims and gutters out. But a star like the sun does something stranger and far grander as it begins to die. It grows, it balloons outward, swelling into a vast glowing giant many times its present size, until it dwarfs the star it once was. The ending of such a star is not a fading at all. It is an enormous, slow expansion. To picture how this happens, you have to look to the core, where the star has spent its whole long life fusing hydrogen into helium. Across billions of years, that core slowly fills with helium ash, the spent remains of the fire, until at last the hydrogen at the very center is all but gone. And here's where things turn surprising. With its central fire faltering, the core can no longer push back hard enough against the crushing weight pressing in upon it. So the core begins to contract, squeezing tighter and growing hotter. But that rising heat kindles a fresh ring of fire in a shell of hydrogen wrapped around the shrinking core. And this new burning shell pours out energy so fiercely that it drives the entire outer body of the star outward in a great swelling tide. The heart contracts and the outer reaches balloon. The star grows vast precisely because, deep inside, it has begun to fail. As it swells, its outer layers stretch thinner and cooler, and a cooler surface glows a deeper, softer red. So the dying giant is not a fierce blue-white blaze, but something gentler to look upon. A huge, ruddy, slowly pulsing globe, glowing the warm color of an ember, vast and calm and strangely beautiful. A star like the sun in this stage can grow to many tens, even hundreds of times its former width. It is a transformation almost beyond imagining. The modest yellow sun we know, blown up into a great red giant that would loom enormous in the sky. And this is where the story turns close to home. For our own sun will one day do exactly this. Some 5 billion years from now, a span so vast it can scarcely be felt, the sun will swell into a red giant, expanding outward across the inner solar system. It will almost certainly engulf the small, scorched world of Mercury and then Venus, swallowing them into its glowing bulk. And the Earth? Our own Earth sits right at the uncertain edge. The sun may well grow large enough to swallow it too, drowning the whole of our world in its slow red fire. Or our planet may, by a narrow grace, escape being consumed, and instead be left scorched and barren, just beyond the giant's reach. Which of these will happen, scientists still genuinely debate, for it depends on subtle things, like how much of its own matter the swelling sun sheds away, and how that loosens its gravitational grip on the planet circling it. We do not yet know the Earth's final fate with certainty, but either way, the gentle world we know will be long gone, transformed utterly by the slow death swelling of the star that gave it life. There is no need to feel any dread in this, though, my friend. The day lies an almost unimaginable distance away, billions of years from now, far beyond not only our own brief lives, but very likely beyond anything we would still recognize as ourselves. It is less a warning than a quiet fact about the deep shape of time, that even the sun, the very emblem of permanence, is living out a story with a final chapter, and that its ending will not be a whimper, but a vast and glowing expansion into the dark. It is a strange thought to rest on, that a thing can grow largest at the very end. We so often imagine endings as a drawing in, a shrinking, a quiet diminishing toward nothing. But a dying star does the opposite. It reaches outward, swelling grander and softer and redder than it ever was in all its long life, filling more of the sky than it ever filled before. Its death is an unfurling. Its ending is an opening out. And so, far in the future, where the small bright sun once hung, there will instead glow a great red giant, immense and unhurried, the warm color of a dying ember, pulsing gently against the dark. A star grown vast in its final age, casting its soft red light across a changed and silent solar system, taking its long, slow time to let go. When a star like the sun dies, it exhales a glowing ring of light into space. There are many ways for a star to come to its end, and some of them are violent, almost beyond comprehension. But the death of a gentle, ordinary star like our own sun is something altogether different. It is one of the loveliest sights in all the universe. A slow, quiet letting go that leaves behind a glowing shell of breathtaking delicacy, like a soul of colored light cast softly into the dark. Here is how it comes to pass. As a star like the sun reaches the very end of its long life, its outer layers grow loose and unsettled, no longer held firmly to the star. And gently, over many thousands of years, the star begins to breathe them away, sloughing off its outermost shells of gas in slow, expanding waves, like rings of smoke drifting outward from a single quiet source. What is left behind at the center is the star's bare, exposed heart, a tiny, fiercely hot core, all that remains of the once mighty star. And that hot core pours out a flood of invisible light, a kind of light beyond the violet edge of what our eyes can see. As that flood washes over the expanding shells of gas drifting around it, it makes them glow, kindling the gas into soft, luminous color, the way a hidden lamp can set a veil of mist alight. The result is one of the most beautiful objects in the heavens. These glowing shells take on the most extraordinary shapes. Luminous rings and globes, delicate hourglasses, soft glowing eyes, intricate nested petals like some cosmic flower opening in slow motion. They shine in tender colors, gentle greens and blues and reds, each one different, each one a fragile work of art, painted in light and gas across the dark. If you have ever seen a photograph of one of these, a great glowing ring hanging in the blackness, or a vast luminous eye with a single bright point at its center, then you have seen the actual death of a star like our sun, captured in its quiet beauty. There is a small curiosity in their name, which says something about how we first came to know them. Long ago, when astronomers first glimpsed these glowing shapes through their early telescopes, they could make out only small, round, softly shining disks. And they thought these looked rather like the pale disks of distant planets. So they called them planetary nebulae, as though they had something to do with planets. They do not. The name was a gentle mistake, born of dim and early eyes, and it has simply stuck through all the years since. These glowing shells have nothing to do with planets at all. They are the cast-off breath of dying stars. Exactly why they take such intricate and varied shapes is still, in part, a quiet mystery. You might expect a star to puff out a simple, even sphere, like a balloon swelling in every direction at once. And yet, so many of these shells are anything but simple, pinched into hourglasses, wound into spirals, sculpted into delicate symmetrical wings. Scientists are still working to understand fully why. They suspect the answer lies in things like the spin of the dying star, or its tangled magnetic fields, or the unseen tug of a companion star circling close by, all of them shaping the outflowing gas as it drifts away. But the full picture is not yet settled, and some of the loveliest of these shapes still hold their secrets. And there is a tenderness, too, in how fleeting they are. For all their beauty, these glowing shells do not last. They drift outward and slowly thin and fade, dispersing into the wider dark over a span of merely tens of thousands of years, the briefest flicker by the measure of the cosmos. The star spends billions of years living, and then, in its dying, paints this one fragile, luminous thing that glows for only a cosmic moment before it scatters and is gone. A brief and beautiful farewell, written in light across the night and then quietly erased. There is something gentle to carry away from this, if you like. We so often imagine death as something dark and grim. But here, at the close of an ordinary star's long life, the universe does something almost impossibly lovely. It takes the ending and makes it luminous. It turns a death into one of the most beautiful sights there is, a soft glow of color unfurling slowly in the dark, fragile, fleeting, and quietly radiant. And so it hangs there for its little while, that glowing shell, a ring or a flower or an eye of softly colored light, drifting gently outward into the black, with one tiny fierce ember of a star glowing at its very heart, slowly fading, slowly dispersing, a last quiet, beautiful breath, exhaled into the dark. A single spoonful of a dead star can weigh more than a truck. It sounds like something invented, a number made up to amaze. But it is simply true, and it describes one of the strangest objects in the universe. The small, dense, slowly cooling ember that a star like our sun leaves behind when its long life is finally over. We call it a white dwarf, and to understand it is to feel the floor of your intuition gently give way. Picture what happens at the very end. A star like the sun, having lived out its life and gently shed its outer layers, leaves behind only its core, the bare, exposed heart of the star. That heart no longer burns. The great fire that sustained it has gone out at last, and with no more energy pouring outward to hold it up, the core has nothing left to resist the crushing pull of its own gravity. So it collapses inward, squeezing down and down upon itself, until something remarkable is left, roughly the entire mass of a star, very nearly as heavy as the sun, packed into a sphere no larger than the earth. Let that settle for a moment. The sun is wide enough to swallow 1,000,000 Earths, and a white dwarf takes very nearly all of the sun's matter and crushes it into a ball the size of our small planet. The material inside is squeezed to a density almost impossible to picture, which is why that single spoonful of it would weigh as much as a heavy truck here on Earth, and why a small bucketful would outweigh a mountain. It is, quite simply, some of the densest matter found anywhere in nature. Now you might wonder, if the fire has gone out and there is nothing burning to push back, what stops the collapse? Why does the core not simply keep falling in upon itself forever, crushed smaller and smaller without end? The answer is one of the deepest and most surprising truths in all of physics. What holds a white dwarf up is something far stranger than heat or fire or any force you would ever meet in everyday life. It is a deep rule from the hidden world of the very small, a law of nature which says that the tiniest particles within the star simply refuse to be packed too closely together. Crowd them past a certain point, and they push back with a fierce and unyielding resistance, not because they are hot, but simply because that crowding is forbidden by the deep rules of how matter is allowed to be. It is a kind of quantum stubbornness, an invisible defiance written into the very fabric of the particles themselves. And it is the one thing standing between the dead star and total collapse, a delicate, ghostly pressure holding up the weight of a whole crushed sun. When a white dwarf is first laid bare, it is searingly hot, glowing a brilliant white from the leftover warmth of the star it once was. But it has no fire left to renew that heat, and so it can only do one thing. Slowly, across the longest stretches of time imaginable, it cools. Like a coal pulled from a dying hearth and set aside, it gives up its warmth little by little into the cold of space, fading gradually from white to yellow to a deep and sullen red, growing dimmer and dimmer over billions upon billions of years. It is a long, patient, gentle fading, the quiet afterglow of a star ebbing slowly toward dark. And there is one more wonder hidden inside these cooling embers, though I will tell it to you carefully, the way the science asks. As a white dwarf cools, the matter deep within it is thought to begin settling into an ordered crystalline pattern, the particles arranging themselves into a vast regular structure, almost as water freezes into ice. Because that interior is rich in carbon, people sometimes speak, with a poet's license, of a dying star slowly turning into something like an enormous diamond in the sky. The truth is more subtle than the lovely image suggests, and the crystal of a white dwarf is not really a jewel you could ever hold in your hand. But the heart of the idea does rest on real evidence. These dead stars do appear to crystallize as they cool, turning slowly, over unimaginable ages, into something solid and ordered and still. It is a strange and quiet fate to sit with. A star that once blazed for billions of years, that warmed worlds and lit up the dark, ending its days as a small, dense, slowly freezing ember, held together by nothing more than a ghostly rule of the quantum world, cooling so gradually that it will go on glowing faintly for longer than the universe has yet existed. There is no violence in it and no drama, only a long, soft fade toward stillness. And so it rests there in the dark, the dead heart of a star, earth-sized, impossibly heavy, glowing faint and patient against the black, slowly cooling, slowly dimming, slowly turning to crystal and quiet, taking all the time in the universe to fade gently toward sleep. There is a kind of star that does not exist yet, anywhere in the universe. This is not because it is rare or hidden or too far away to see. It is because the universe itself is still far too young to have made even a single one. These stars are written into the laws of physics, predicted with quiet confidence, waiting in the deep future, and yet not one of them has ever existed in all the time that has passed since the beginning. We call them black dwarfs, and to understand them is to peer further into the future than almost anything else we know how to imagine. To see where they come from, picture the small ember that a star like our sun leaves behind when it dies. After such a star has lived out its long life and gently let go of its outer layers, what remains at the center is its bare, exposed heart, a small, dense, fiercely hot sphere, roughly the mass of the sun packed into a ball no bigger than the earth. When it is first laid bare, this dead heart glows a brilliant white, lit by all the leftover warmth of the star it once was. But its fire has gone out. It makes no new heat, and so it can only do one thing across the long ages to come: cool. It cools the way a coal cools after it is lifted from the fire, giving up its warmth slowly into the cold around it. But a dead star is so hot and holds its heat so stubbornly that this cooling takes a length of time almost beyond comprehension. It fades over billions of years from white to yellow to orange to a deep and sullen red, dimming all the while. And then it keeps fading, growing redder and dimmer still for longer and longer stretches of time. Only at the very end of this almost endless cooling, when the last of its warmth has finally drained away and it no longer glows at all, not even faintly, does it become a black dwarf, a cold, dark, silent sphere, the fully extinguished cinder of a star. Now here is the part that is difficult to hold in the mind. How long does it take for a dead star to cool all the way down to darkness like this? The answer is something on the order of 1,000 trillion years, perhaps even longer. It is a span of time so vast that our ordinary words begin to fail us. And the universe, as best we can tell, has so far existed for only about 14 billion years. Set those two numbers side by side and you find that the universe has lived through only the tiniest sliver of the time it would take for even one black dwarf to form. Not a fraction of a percent. Far less than that. And so the simple, astonishing truth is this: there are no black dwarfs. Not one. Anywhere in all of existence. Every single dead star that has ever formed in the entire history of the cosmos is still warm enough to glow, still slowly cooling, still ages upon ages away from going fully dark. The black dwarf is real in our understanding and certain in our physics, and yet it remains, for now, purely a thing of the future. A kind of object the universe has simply not yet had the time to create. There is something quietly profound in that, if you let yourself rest on it. We are so used to thinking of science as the study of what is, of stars we can see, of things that are out there right now. But here's a thing that we can describe in detail and speak of with confidence, that has never existed and will not exist for an almost unimaginable stretch of time. It is less a discovery than a kind of prophecy, a glimpse of the deep, deep future of the universe, when the bright era of shining stars has long since passed, and the dark, cold cinders of dead suns drift quietly through a far older and dimmer cosmos than the one we know. Picture that far-off time, if you gently can. The galaxy's grown ancient, the last of the bright stars long since burned out, and scattered through the immense dark, the cold black embers of stars that died unthinkable ages before, sphere after silent sphere, no longer glowing, simply drifting, holding the last cold memory of the fire they once were. It is a vision of an almost perfect stillness, waiting at the far end of time. But not yet. For now, every dead star in the sky is still glowing, still warm, still slowly fading through the long red twilight of its cooling. The great darkness lies ahead of them, an eternity away. And so the black dwarfs wait, patient and unborn, in a future so distant that the universe itself has scarcely begun the journey there. Not gone, not yet here, only waiting quietly in the deep future for a cold that has not yet come. A star's entire fate comes down in the end to a single number. It is a strange and beautiful thing that the universe should work this way, that whether a dying star fades away in gentle peace or tears itself apart in unimaginable violence should be decided so cleanly by something as simple and exact as a number. But it is true. There is a precise line drawn across the masses of the stars, and which side of that line a star falls on determines, with almost no room for argument, how it will meet its end. To understand the line, you have to picture what holds up the dead heart of a star. When a star like the sun dies, its core is left behind, no longer burning, with nothing left to push back against the crushing weight of its own gravity. You might think it would simply collapse away into nothing, but something stops it, something strange and quiet, drawn from the hidden rules of the very small. Deep within that crushed matter, the tiniest particles refuse to be packed too closely together. Press them past a certain point, and they push back with a fierce and unyielding resistance, not because they are hot, but simply because nature forbids them to be crowded any tighter. It is this quiet defiance, this refusal of the smallest particles to be squeezed beyond a certain limit, that holds the dead star up and keeps it from falling in upon itself. But that resistance has its limits. It can hold up only so much weight. And this is where the magic number comes in. If the dead core weighs less than about 1.5 times the mass of our sun, then that quiet quantum stubbornness is strong enough to win. The core settles into a stable, dense ember, and it will simply rest there, cooling slowly and gently, for ages upon ages. A peaceful death. But if the core weighs even a little more than that, more than roughly 1.5 suns, then the weight becomes too great. The stubborn resistance of the particles is overwhelmed. It can no longer hold, and the core, having lost its last defense, collapses catastrophically in a fraction of a second, setting off one of the most violent events the universe has ever known. 1.5 times the mass of the sun. That is the line. On one side, a gentle fading into the long dark. On the other, a cataclysm. The whole difference between a quiet ending and a violent one rests on whether a dying star carries a little less or a little more than that single quantity of matter. What I find most wonderful about this number is the story of how we came to know it. It was worked out nearly a century ago by a young man of just 19 or 20 years old. He was traveling by ship from his home in India to study in England, a long sea voyage of many days across the open ocean. And somewhere out on that water, with nothing but the waves around him and time on his hands, this young man took up his pen and worked through the mathematics of how a dead star holds itself up, and found, to his quiet astonishment, that there was a limit, that above a certain mass, no dead star could survive. He had glimpsed the very line that divides the fates of the stars, and he had done it as a teenager, alone, at the rail of a ship in the middle of the sea. For a long while, the great and established scientists of the day did not want to believe him. The idea seemed too strange, too troubling, that a star could be doomed by its own weight to collapse beyond all saving. His result was doubted and dismissed and argued against. But the young man's mathematics was sound, and the universe, it turned out, agreed with him. We call it the Chandrasekhar limit now, after that young man at the rail of the ship, and it stands today as one of the deep and settled truths of how stars live and die. There is something that stirs the heart in that image. A young person, far from home, catching sight of a profound and hidden truth that the wisest minds of the age had missed, simply by following the mathematics wherever it led. It is a quiet reminder that the universe keeps even its deepest secrets out in the open, waiting, and that sometimes it is the patient and the unafraid who first catch sight of them. And the number itself goes on, quietly governing the heavens, indifferent to who found it. Every star that has ever died has been sorted by it, without exception, weighed against that single threshold and sent toward one fate or the other. A gentle line, drawn by nature across the masses of the stars, dividing all the dying suns in the sky into the peaceful and the violent. Exact, silent, and settled long before any of us were ever here to wonder at it. For a few weeks, a single dying star can outshine an entire galaxy. Think about what that means. A galaxy holds hundreds of billions of stars, a vast city of suns spread across distances the mind can barely hold. And yet when one giant star comes to the end of its life and explodes, that single death can blaze so brightly that for a little while it pours out more light than all those hundreds of billions of stars put together. One point in the dark, briefly outshining everything around it. This is a supernova, and it is among the most violent and most magnificent events the universe has ever produced. It happens only to the giants, the great massive stars, many times heavier than our sun, that burn through their lives in a furious blaze and die young. Such a star spends its whole existence holding itself up by the outward push of the fire at its core. But when that fire finally falters and goes out, there is nothing left to resist the inward crush of the star's own colossal weight. And so the core collapses, not slowly and not gently, but all at once, falling inward upon itself in less than a single second, an entire core's worth of matter plunging together at a sizable fraction of the speed of light. Then it stops, abruptly and violently. The collapsing core slams into itself and is crushed about as far as nature will allow, becoming, in an instant, almost impossibly rigid and dense. And the rest of the star, still rushing inward, slams down onto that suddenly unyielding heart and rebounds. A titanic shock tears back outward through the body of the star, and in a matter of moments the whole vast outer bulk of it is blown apart and flung into space, hurled outward at speeds that scatter the wreckage across light years. The star is torn open, and its insides are cast out into the dark in a flash of light, bright enough to be seen clear across the universe. And here's the part that turns this violence into something almost sacred. In the unimaginable heat and pressure of that explosion, new elements are forged, heavier kinds of matter cooked into being in the fury of the blast, and then they are scattered outward, seeded into the surrounding darkness, mingling into the thin gas that drifts between the stars. The iron and the other heavy materials that come to wander through space, that one day gather into new worlds, that become the very stuff of planets and oceans and living things. Much of it is born here, in the death explosions of giant stars. The most violent ending in all of nature turns out to be one of its most creative acts. A star tears itself apart, and in doing so it sows the seeds of everything that will come after. These explosions are rare in any one galaxy, flaring up only now and then across the long centuries. But every so often one has blazed close enough for human eyes to witness. Nearly 1,000 years ago, in the year 1054, watchers of the sky in China and elsewhere recorded the sudden appearance of a brilliant new star, so bright that for several weeks it could be seen even in broad daylight, shining against the blue. Then slowly it faded, and after a time it vanished from view altogether. What they had seen was a giant star dying, a supernova, far across the galaxy. And if you look today at the very place in the sky where that new star once blazed, you find a beautiful, tangled cloud of glowing wreckage, still drifting outward into space, nearly 1,000 years on, the scattered remains of that ancient death. There is something that stirs deep in the chest at the thought of it, that a star's death could be so bright that ordinary people would stop and stare and write it down 1,000 years ago. That the same explosions which tear stars apart are the very forges that made the iron in our blood and the calcium in our bones. The universe builds its most precious things in its most violent moments, and then scatters them gently across the ages, waiting for them to gather again into something new. And so it blazes, for its little while, a single dying giant, brighter than 100 billion suns, a fierce new point of light hanging in the dark. And then slowly, over the following weeks, it dims and softens and fades, settling at last into a quiet, expanding cloud of glowing debris drifting outward into the night. A death that lit up the heavens, sinking gently back into the dark, leaving its scattered gifts behind. At this very moment, trillions of ghostly particles are passing straight through your body, and you cannot feel a single one. They stream through you constantly, silently, by the countless trillions every second, tiny phantoms of matter pouring out of the sun and racing across space in every direction. They pass through your skin, through your bones, through the chair beneath you and the ground below that, as though none of it were even there. Most of them sail straight through the entire Earth, in one side and out the other, without ever once touching a thing. We call these particles neutrinos, and they are among the faintest, shyest, most ghostly things in all of nature. What makes them so ghostly is that they barely interact with ordinary matter at all. The solid world around you, which feels so firm and impassable, is to a neutrino almost entirely empty space, and it slips through the gaps with ease. You could line up a wall of solid lead stretching for light years, and a great many neutrinos would still pass clean through it without so much as a flicker. They are real. They carry energy. They are pouring through you right now as you rest, and yet they touch us so rarely, so faintly, that for almost all of history we never even knew they were there. And those neutrinos come to us straight from the deepest place there is. Every time two bits of matter fuse together in the sun's core, a neutrino is born. And because almost nothing can stop it, it flies directly out of the sun's heart and across space to us, untouched, in a matter of minutes. Think of what that means. The light of the sun is shaped and scattered and slowed on its long way out, but a neutrino carries an unspoiled message from the very center of the star, the one kind of messenger that can reach us directly from a place we could never hope to see with our eyes. When these ghostly particles pass through you, some of them have come, unhindered, all the way from the fiery core of the sun itself. But their shyness hides something remarkable. Because neutrinos pass through nearly everything, they can carry news out of places that nothing else can escape. And the most extraordinary place they escape from is the very heart of a dying star. When a giant star collapses and explodes, the violence at its core is beyond all imagining. And in that collapse, an almost incomprehensible flood of neutrinos is created, so many of them, and carrying so much of the dying star's energy that they make up the overwhelming bulk of everything the explosion releases. Nearly all of the titanic energy of a star's death pours out, not as light but as this silent torrent of ghost particles, fleeing the catastrophe at almost the speed of light. The light we see, brilliant as it is only a small leftover. The true story of the star's death is told in neutrinos, and once we managed to catch them. In the year 1987, deep inside detectors buried far underground, scientists recorded a faint, sudden burst, just a couple of dozen of these ghostly particles, arriving together in the space of seconds. They had come from a giant star that had exploded in a small neighboring galaxy, far across the gulf of space, after traveling for something like 160,000 years to reach us. For the first time in all of history, human beings had caught the ghosts fleeing a dying star. And here is the detail that gives me a gentle chill. Those neutrinos arrived a few hours before the light of the explosion did, because they slipped straight out of the collapsing core and flew directly toward us. While the light had to struggle its way up through the star's outer layers, the silent ghosts reached us first. The faint, early heralds of the catastrophe, carrying the news ahead of the blaze. Just 24 tiny particles after a journey of 160,000 years. And from those few faint ghosts, we learned that our understanding of how giant stars die was right, that the heart of such a death really does pour out its energy in this silent, invisible flood. A mere handful of phantoms caught deep underground, confirming the hidden inner workings of a dying star 160,000 years and a whole galaxy away. There's something quietly staggering in that. All around us, all the time, this ghostly traffic is passing. Neutrinos from our own sun pouring through us by the trillions every second, and among them, ever so rarely, the faint whispers of distant stars dying in the dark. We move through an unseen storm of these gentle phantoms, utterly unaware, our bodies no more an obstacle to them than a clear window is to light. The universe is far busier, and far more crowded with quiet messengers than our senses could ever tell us. And so they pass through you now, in this still moment, countless silent ghosts, weightless and unfelt, streaming out of the sun and in from the depths of space, carrying within them the news of fire and collapse from places unimaginably far away. Through your hands, through your heart, through the whole sleeping earth, and out the other side, never pausing, never touching, simply passing through, on and on into the dark. Imagine taking the entire sun and crushing it down until it would fit inside a single city. It sounds impossible, and yet the universe does exactly this. When certain giant stars die, they leave behind a remnant so dense, so unimaginably compressed, that it defeats every instinct we have about how matter is supposed to behave. An entire star's worth of material, more mass than our whole sun, squeezed down into a ball only a dozen miles or so across. A star shrunk to the size of a town. We call it a neutron star, and it is one of the strangest things that exists anywhere in nature. The numbers are almost impossible to feel. Take a single spoonful of the material inside a neutron star, just a small scoop, the size of a sugar cube. And here on Earth, that tiny piece would weigh about as much as an entire mountain. One sugar cube. As heavy as a mountain, the matter has been crushed so tightly that the empty space inside ordinary atoms has been almost entirely squeezed out, leaving behind something so dense that our usual words for heavy stop meaning very much at all. If you could somehow hold a mere thimbleful of it, the weight of all of humanity put together would be resting in the palm of your hand. How does something like this even come to be? When a giant star collapses at the end of its life, the crush of gravity becomes so ferocious that it forces the tiny pieces of matter together far harder than anything we could ever hope to reproduce. The particles inside are jammed so tightly against one another that they merge and transform, and what is left is a single, smooth, almost unimaginably dense sphere, held up, just barely, by the last desperate refusal of its particles to be packed any tighter still. It is gravity and the deep rules of the very small locked together in a standoff at the very edge of what is possible. A whole sun's worth of matter balanced on the nice edge of total collapse. And the strangeness only deepens the closer you look. The pull of gravity at the surface of a neutron star is so ferocious that it beggars belief. Hundreds of billions of times stronger than the gentle tug that holds you to the Earth. A pebble dropped from even a small height would strike that surface faster than anything we could ever hope to launch. To lift yourself the height of a single step, there would demand more effort than scaling the tallest mountain on Earth. And wound around many of these stars are magnetic fields of almost incomprehensible power, trillions of times stronger than our own planets, invisible and immense, threading out into the dark around them. Everything about these objects sits at the very outer edge of what nature seems willing to allow. And then there is what these objects do, which is perhaps stranger still. Many neutron stars spin, and not gently. Picture a whole crushed star, heavier than the sun, turning round and round many hundreds of times every single second, a blur of impossible motion. As they spin, some of them sweep beams of energy out from their poles, sending those beams turning around and around, like the light of a lighthouse wheeling in the night. And if one of those beams happens to sweep across the Earth, then once with every single turn of the star, a faint pulse reaches us, flick, 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 arriving with a steadiness so astonishing that these spinning stars keep better time than almost any clock we have ever built. When the first of these steady pulses was discovered, long ago, it was so regular, so precise, so unlike anything anyone expected to find in the natural sky, that for a brief and wonderful moment the scientists who found it half wondered whether they might be hearing a signal from some distant civilization. They even nicknamed it, half in jest, after little green men. But it was no message from anyone. It was something far stranger and grander, the dead, spinning heart of a giant star, sweeping its beam across the cosmos, keeping its perfect, tireless time, entirely on its own. There is something that quiets the mind in the thought of these objects, that nature can take a whole star and crush it into something the size of a city, so dense that a spoonful outweighs a mountain, and then set it spinning hundreds of times a second with a steadiness beyond any machine. And that there are countless such objects out there, scattered through the galaxy, turning silently in the dark. The universe holds extremes so far beyond our everyday world that we can barely find the words for them, and yet they are real, and they are out there, right now, keeping their faithful time. And so it spins on, in the deep dark, that impossible sphere, a whole sun crushed into the space of a city, turning and turning, sweeping its quiet beam across the emptiness. A lighthouse no one built, keeping watch over nothing, counting out the moments with a patience that will outlast almost everything. Round and round in the silence, faithful and strange in the long dark between the stars. When the very largest stars die, they fall and never stop falling. Most dying stars, however violent their end, leave something behind, a dense ember, a spinning remnant, some final object resting in the dark. But the most massive stars of all do something stranger and more absolute. When such a giant reaches the end of its life and its core collapses, there is no force left in all of nature strong enough to halt the fall. Nothing can stop it. The core simply keeps collapsing, inward and inward, smaller and denser without limit, until it has crushed itself down past the point of all return, and what it leaves behind is a black hole. A place where gravity has won so completely that not even light can escape. To picture what that means, you have to think about what it takes to leave something behind. Throw a ball up into the air and it slows and stops and falls back because the Earth's gravity pulls it home. Throw it hard enough, fast enough, and it could escape into space entirely. Every object has a certain speed you would need to reach in order to break free of its gravity and never fall back. For the Earth, that speed is very fast, but reachable. For the Sun, faster still. But for a black hole, gravity is so overwhelmingly strong that the speed you would need to escape it climbs past the speed of light itself. And since nothing in the universe can travel faster than light, nothing at all can escape. No rocket could ever power its way back out, and no ray of light can flee it either. Once something crosses that fatal boundary, there is no coming back, ever. That boundary has a name. It is called the horizon, a sphere of no return surrounding the black hole, unmarked and invisible, but utterly absolute. Outside it, escape is still possible. Cross it, even by a hair, and you are bound forever to fall inward, with no path back to the universe you came from. It is less a surface than a threshold drawn in empty space, a line beyond which the very word out simply ceases to have any meaning. And here's one of the strangest and most haunting things about that boundary. Suppose you could watch from a safe distance as something fell toward a black hole, a glowing object drifting slowly in. You would expect to see it fall in and vanish, but that is not what you would see. Instead, as it neared the horizon, you would see it appear to slow down. The closer it drifted to that fatal edge, the more it would seem to linger, its motion stretching out, its light growing dimmer and redder, and at the very horizon itself, it would appear to freeze, hanging there, fading, slowing, never quite crossing, its final moments stretched out toward forever before your eyes. Time itself runs differently in the grip of such gravity, and from the outside, the last instant of the fall seems to take an eternity. The black hole keeps frozen at its very edge, a kind of fading ghost of everything that has ever fallen toward it. I should be honest with you about something, my friend, because it is part of the wonder. What happens deep inside beyond the horizon, we do not truly know. Our finest theories tell us that everything rushes toward a central point of unimaginable density. But at that point, the very laws of physics that have carried us all this way stop making sense. The mathematics breaks down. It hands us answers that cannot be real, and quietly admits that here, our understanding has reached its edge. The inside of a black hole is one of the few places in all the universe where we must simply say, we do not yet know. There is a deeper truth waiting there, some law we have not yet found. And until we find it, the heart of a black hole remains a genuine mystery, perhaps the deepest one there is. There is something humbling and strangely peaceful in arriving at that edge. We can follow the lives and deaths of the stars all the way to this final place, the most complete ending that matter can have. And here, at last, the universe keeps a secret we cannot yet read. A perfect darkness ringed by the gently bent and glowing light of everything behind it, holding within it we know not what. And so it rests there in the deep dark, silent and absolute, a sphere of pure shadow, the final remnant of a once blazing giant, bending the light of distant stars softly around its unseen edge. The quietest place in all of creation. The one ending from which nothing returns, keeping its ancient secret, patient and still in the long night between the stars. Nothing in the universe is ever truly lost. When a star dies, whether it fades into a quiet ember or tears itself apart in a final blaze, it does not simply vanish from the story. The matter it was made of, the elements it forged across its long life and in its death, are not destroyed. They are released, scattered outward into the dark, mingled back into the thin drifting gas that fills the spaces between the stars. And there, slowly, patiently, over ages, they wait, until one day, gathered up by gravity, they begin to come together again. And out of the remains of stars that died, new stars are born. This is the great cycle that turns at the heart of everything. And once you see it, you can never quite unsee it. Each generation of stars lives and shines and dies, and in dying enriches the darkness with the elements it made. The next generation forms from that enriched material, inheriting the gifts of all the stars that came before. And those new stars in their turn will live and die and give themselves back again, seeding the dark for the stars that follow. Birth and death are not opposites here, not enemies. They are two halves of a single turning wheel, each one endlessly feeding the other, around and around through all the long ages of the cosmos. And the gentle truth, the one I would most like to leave resting in your mind, is that you are part of this wheel. The sun overhead was built from the scattered remains of older stars, stars that lived and died before it was ever born. The earth beneath you was gathered from that same enriched material, and your own body, the iron carrying breath through your blood, the calcium holding up your bones, the very atoms that make you, all of it was forged inside stars that died long ago, scattered into the dark and gathered up once more across billions of years into the shape of you. You are not separate from the life and death of the stars. You are one of its passing forms. A way that old starlight has for a little while of gathering itself together and looking up at the sky it came from. There is a deep comfort in that, if you let it settle over you in the quiet. We tend to think of endings as final, as a vanishing into nothing. But the universe does not seem to work that way. In the great cycle of the stars, an ending is only ever a turning, a giving back, a scattering of gifts, a setting of the stage for something new. The dust of dead stars becomes the heart of living ones. The remains of one generation become the substance of the next. Nothing is wasted. Nothing is lost. It only changes and moves on and becomes part of whatever comes after. And this turning has happened many times over already. The atoms that make you up did not come from just one star, but quite possibly from several, passing through cycle after cycle, gathered and scattered and gathered again across spans of time too long to truly feel. Each atom in your hand is a traveler with a history far longer than the earth itself, a quiet veteran of the wheel, having been part of who knows how many stars and clouds and worlds before it ever became, for this brief moment, a part of you. You are not standing at the beginning of this story, nor at its end. You are one turn of a wheel that has been spinning since long before the sun, and that will go on spinning long after. So when you look up on some clear night at all those distant points of light, you might remember that you are not a stranger gazing at something far away. You are looking at your own family, at the very kind of thing you are made of, at the long lineage of fire and dust that you yourself belong to. The stars and you are part of the same unbroken story, the same slow wheel of dust becoming light and light becoming dust, turning quietly across more time than the mind can ever hold. And it is still turning now, this very moment, in every corner of the sky. Somewhere, even as you rest, old stars are letting go of the elements they made, breathing them out softly into the dark. And somewhere else, in some cold and quiet cloud, those scattered gifts are gathering together once more, beginning the slow fall inward that will one day become a new star, and perhaps new worlds, and perhaps in time new wanderers to look up and ask where it all came from. You are made of stars that died so that you could be here. And one day, far beyond all of this, the atoms that are you now will move on again and become part of something new in their turn. There is no ending in that, only the long, gentle turning of the wheel, dust to starlight, and starlight to dust, around and around through all the quiet ages of the universe. Rest now, beneath it all. You are a small, warm gathering of ancient starlight, held together for a little while, here in the dark, and the great slow wheel turns on, as it always has, carrying you gently with it among the stars. And here, gently, our journey among the stars comes to its end. If you are still awake, drifting somewhere in the quiet with me, there is no need to stir. Another story is waiting whenever you would like it, another slow wander through the wonders of the cosmos, ready to carry you onward into the dark. Let it begin when you are ready, and simply close your eyes again. And if sleep has already found you, then let it keep you. You have nowhere to be and nothing to hold on to. The stars will go on turning patiently far above the soft and sleeping world, just as they always have and just as they always will. Rest now, my friend. You are a small, warm gathering of ancient starlight, safe here in the dark. Sweet dreams among the stars.